Welcome back. In the last few videos we have seen how to solve the Laplace equation, steady state or the steady state heat equation. So, the last video we have seen how to solve the Laplace equation in a rectangular domain. We can solve the Laplace equation in a kind of strip kind of thing. It is rectangular, but it is a strip. Okay. So, we will just I will give you that remark and I may give you as an exercise that problem, and then we will solve Laplace equation in circular domains. Okay. We will just look into this to do that. So, what I want to say is, see, you have a finite thing. So, this is 0 a as a x domain, you have a finite, and you can close this here. So, you can consider this as a domain y equal to 0. So, x is between 0 to a, y is between 0 to infinity. So, if this is your y axis and this is your x axis, x is between 0 to a and y is actually greater than 0. So, in this domain, this is your domain where you have a Laplace equation is satisfied, and then on this you provide some boundary condition. So, that means u, so gradient square u equal to 0, and u at x y 0 is given as some f on x, and here because the steady state heat equation, so you want the temperature at infinity will be 0. So, you can give that infinity condition. So, if you give, then only you will have a solution exists, u goes to 0 as y goes to infinity. Okay. So, that is what you can give. So, for all x between 0 to a, so this is the boundary kind of boundary condition at infinity. Okay. So, that means you need you cannot allow non-zero solutions at infinity. So, if you do that and you give the boundary condition here, so that is u at x is 0 and y is g1 of y, and u at a y equal to g2 of y. So, this problem also you can handle similarly in a similar way that I have solved the Laplace equation for a rectangular domain. So, the idea is you find this, you make this 0 conditions, you make this 0 condition. So, make this 0. So, that is what we have seen last or you just for this you have to give 0 boundary condition, because this contributes where you have finite places x equal to 0 and x equal to a, you should have a Sturm-Liouville problem. So, that is why you should have a homogeneous boundary conditions. If you give these boundary conditions, then you can solve in this semi infinite strip. So, how do we do this? So, you extract a problem for x of x, which is for with the boundary condition x of 0 is 0 and x at a is also 0. Okay. And then once you solve this and you get the eigenvalues and eigenfunctions, corresponding y of y you can find out the general solution. Okay. And you find the general solution with lambda. So, and then you apply as y u goes to 0 as y infinity. So, for that, so that you can remove one arbitrary constant. So, you will have, because of this boundary condition, you will only get for each eigenvalue you will have only one arbitrary constant for each n. Suppose lambda n, for each n lambda n you have a n as an arbitrary constant. So, that arbitrary constant you can get it from this boundary condition. So, with that, so in that sense separation of variable method can be applied for this semi infinite domain for the Laplace equation, though it is a rectangular. So, we use only Cartesian coordinates. Okay. This is what I may give you as an exercise. So, you can also work out if you want, if you are interested you can just simply work out. Okay. So, today we will just look at the Laplace equation in a circular domain. So, if you want to use circular domains, you have to convert this Laplace equation into polar coordinates. So, we have seen that x equal to r cos theta, r sin theta are polar coordinates. So, that r is positive and theta is between 0 to 2 pi. Okay. So, you have a new variables r and theta. So, if you convert this del square u, so del square u, that is uxx plus uyy equal to 0. So, this becomes, so Laplace equation becomes, with these new variables you have urr plus 1 by r ur plus 1 by r square u theta theta equal to 0. So, that is what is the Laplace equation, r positive and theta is between 0 to 2 pi. So, this is a Laplace equation in the full plane. Okay. So, now we will just look at the general problem boundary general domain. So, I will just consider. So, you cannot solve all domains, so only circular domains. For example, you can solve this equation in this circle, inside the domain is D here, or you consider exterior circle, exterior of the circle, that is D is your outside. So, that still the boundary is same, this is the boundary, okay. This is the boundary here, so here also this is the boundary. So, to get this kind of two things, two domains, this is one particular problem, okay, this is a second problem. So, if you want to solve this Laplace equation in the domain D, okay, and you give the boundary condition on the on B. So, considering this as the domain, D is here, domain is here outer exterior of this circle, and here interior of the circle. So, D is interior of the circle. So, these are the two problems. So, in the two domains you can solve this Laplace equation, and to do this we give a general. So, these are just a particular case, as a particular case you can get out of a general problem, general domain. So, that I consider as an annulus region. So, let me consider some annulus region, that is where my D is. D is here, this is 0, and you have this with R1 and this with length R2, two circles, okay. So, your domain is D. So, your boundary is this is your boundary B, and also this interior inside, this is also your boundary, okay. So, B is basically boundary inside, inner circle and outer circle, okay. So, we will solve this equation. So, the problem for 3, the domain 3, if you do this 1 and 2 will be particular cases, as a particular cases you can get it. So, let me write the problem for this annular region. So, Laplace equation in an annulus region, okay. So, let me write this. So, you take the same Laplace equation, so in polar coordinates, u r r plus 1 by r u r plus 1 by r square u theta theta equal to 0. Now, what is your r? So, the domain is D. So, r is between r1 and r2. So, that is the region D, and theta is always because it is a circular domain. So, you have 0 to 2 pi. So, that is your, so you have this includes 0 to 2 pi, okay. So, this is the domain over which you have the Laplace equation is given. Now, if you want to give boundary data, so what is the boundary data you want to give? So, you simply give the Dirichlet data. So, you provide a temperature on the boundary, that is u at u of x y equal to some. So, you can see that this is only function of this, r is fixed here, okay. So, that is u at r2 theta. So, it is a function of theta, r2 is fixed, okay. R is fixed here on this domain because it is a circular domain. So, it should be some f1 of theta, okay. So, let us call this f2 of theta. So, that inside here, inside also you can provide. So, where u at r1 theta, on the inner circle you can provide as f1 theta. So, these are the two domains, this is the boundary data where theta is between 0 to 2 pi. So, you can provide that. So, you have u of r1 theta is f1 theta, and u at r2 theta is f2 theta. So, that is what is the theta is between 0 to 2 pi. So, with these are the boundary conditions. So, this is your Laplace equation. You want to solve this equation. So, to do this we will just work out the solution by the separation of variables method. So, again let with solution let u of r theta. So, now you have the variables r and theta as capital R of r as a function of r, and capital theta of theta, let us call this way, as a non-zero solution. So, you assume that this is a non-zero solution. Then if this is the solution of this Laplace equation, is just simply substitute. If you substitute into this equation, what you see is r double dash of r theta of theta plus 1 by r, u r is r dash of r and theta of theta plus 1 by r square r of r into theta big theta double dash of theta equal to 0. So, that is what is the equation become. Now, from this you can separate this r and theta variables by just dividing with r of r into theta of theta, that is the solution which is a non-zero solution. So, you can divide both sides. So, if you do that, what you are left with is r double dash of r by r of r plus 1 by r times r dash of r by r of r, because theta of theta gets cancelled. So, plus 1 by r square, r of r goes, now you have theta double dash of theta divided by theta of theta equal to 0. So, what I do is I take this to this side minus, I bring this r square here. So, you have r square here. So, you multiply r square. Okay. So, you simply write like this first of all. So, if you want, so you bring this r square here. So, if I remove this, bring this r square here. So, you have r square. And so, you have r square, r goes. So, you are left with only 1 r. So, this is what you have. Okay. So, these are functions of r, these are functions of theta. So, this should be a constant. Okay. Unless they are constant, it cannot be same, because there are two functions of two different variables, two independent variables r and theta. So, this is what you have. So, the Laplace equation becomes two ordinary differential equations. One is r square r double dash of r plus r dash of r, this r of r into lambda. So, that becomes plus lambda plus lambda into r of r equal to 0. This is one equation, one ordinary differential equation. Other is theta double dash of theta minus minus. So, you better you make this minus here. So, okay, bring this minus here. So, you make it plus, so that you have a minus here. So, that this Sturm-Liouville problem for theta, what you get is minus equal to minus lambda theta of theta equal to 0. So, theta is between 0 to 2 pi, and here r is between r1 to r2. Okay. So, we extract a Sturm-Liouville problem for theta, because you can see that theta is between 0 to 2 pi, and what are the conditions? You do not have a boundary conditions. You have to look at this figure and you see that is a circular domain. So, theta at 0 and theta 2 pi both are same. So, they are basically, and it satisfies the Laplace equation. So, it is the derivatives are also continuous. Okay. You differentiate, and with respect to theta they are actually continuous. So, you can see that u theta is actually continuous, theta derivative is twice differentiable. So, u theta is continuous and u is also continuous. That means, as a theta, as a function of theta, it should be continuous variable. So, if you use that, or you simply think of this way. So, u of boundary conditions are like u of r theta, which is r of r, and theta of theta. So, you put the r theta as 0, this should be same as r of r theta of 2 pi. Okay. The same way u dash of, so that is u dou u by dou theta is also continuous at r theta. Theta is 0, should be same as dou u by dou theta at r 2 pi. So, both are same. So, this will give me, so this first of all this will give me theta at 0, this is 0, okay, theta 0. So, you should write u r at 0 should be same as u r at 2 pi, because it is a circular domain, so it is a periodic domain. So, this will give me this. So, r r goes, what you get is 0, theta at 0 is same as theta at 2 pi. Okay. This is one boundary condition for this Sturm-Liouville problem. So, similarly, so these are intrinsic, is not, these need not be given, okay, that you should you getting it from the, because of the circular domain you can easily see this one. So, if you use this one, r of r theta dash at 0 should be same as r of r times theta dash at 2 pi. So, this will give me r goes both sides, this, okay, this cannot be 0. So, r because it is a function of r, you can should be non-zero. So, it should be cancelled. So, you get theta dash of 0 equal to theta dash at 2 pi. So, these are periodic boundary conditions that we set for periodic Sturm-Liouville system. So, periodic Sturm-Liouville system is a regular type of equation with these boundary conditions. If you give these periodic boundary conditions, it will become periodic Sturm-Liouville system. What we got is periodic Sturm-Liouville system, periodic Sturm-Liouville system, that is theta at theta double dash of theta minus lambda theta of theta equal to 0, theta is between 0 to 2 pi, and theta at 0 equal to theta at 2 pi. This is one periodic boundary condition, and other one is theta dash at 0 is same as theta at dash at 2 pi. So, these are the periodic boundary conditions. Okay. So, this is a periodic system. So, which we know already. So, is already in self adjoint form. So, we have seen, just look back the video on periodic Sturm-Liouville system. So, in the Sturm-Liouville theory we have seen that this is exactly periodic system we solved. Okay. So, the eigenvalues are basically eigenvalues. So, eigenvalues I write directly, eigenvalues are lambda equal to n. Okay. So, you see that lambda is n and eigenfunctions are let us call this theta n. So, lambda n I call it n is running from 0, 1, 2, 3 onwards. Okay. And then theta n of theta is actually equal to, so eigenfunctions are cos n theta and sin n theta. Okay. So, n is running from 0, 1, 2, 3 onwards. So, when you put n equal to 0, cos n theta is 1 and sin n theta is 0. So, what you effectively, it is for n equal to 0 only one eigenfunction remains, for n equal to 1, 2, 3 onwards you will have 2 eigenfunctions. So, these are all already, because 0 to 2 pi is already orthogonal. So, they are self adjoint, they are actually complete orthogonal set of eigenfunctions. So, this is what we have seen in the Sturm-Liouville theory. So, the dot product of these functions theta are the solutions of this Sturm-Liouville system phi psi, as usual this is 0 to 2 pi and phi x and psi bar of x dx. They are all real valued functions, so bar does not matter. So, this is the definition of the dot product, because this is a periodic Sturm-Liouville system 0 to 2 pi. Okay. So, with this, so you know that these are the eigenvalues lambdas are n. So, once you know the lambda, you put here as a lambda equal to n and try to see what happens. So, when you put lambda equal to n, so actually what you get is I think I made a mistake, should be n square. So, when lambda equal to n square, you will get actually minus n square you will get. Okay. For lambda equal to minus n square, you will get cos n theta sin n theta as the solutions. Okay. So, these are the eigenvalues. You can look back into these periodic Sturm-Liouville systems. Okay. In the earlier videos you see that these are your eigenvalues and these are your eigenfunctions. So, lambda n you get as a minus n square. So, if you go back and put it here, okay. So, you can see that minus of this equal to lambda. So, what you get is this will be plus. So, this is the equation, this ordinary differential equation, this is actually a kind of Euler-Cauchy type equation. So, we will write it here. So, r square capital R double dash of r plus r times capital dash of r plus what you have is plus lambda r of r. So, lambda is a minus n square. So, I can put minus n square r of r equal to 0, r is between r1 to r2. So, what is its solution? This is the Euler-Cauchy type equation. Okay. This is the Euler-Cauchy type equation. This is Euler-Cauchy type equation. The reason is you have y double dash of x, the product, the coefficient is x square. So, you have a y dash of x, this is coefficient is x. So, r into r dash of r, and here you have a y with a constant. So, this is Euler-Cauchy type equation. So, the solution you should look for is y of x equal to x power m. Okay. So, in the same way here r of r, so let r of r be r power m. Then if you look for solution in this fashion, so if you substitute into that equation, so what you get is r power m times m into m minus 1, if you replace here. If you put r dash, so the m into r power m minus 1, this r goes. So, you still again you will get r power m into m minus again r power n is to substitute, that is common. So, minus n square equal to 0. So, what you get is goes, what you get is m square minus n square equal to 0. So, n we know that n is actually 0, 1, 2, 3 onwards. So, m is equal to plus or minus n. So, 2 roots if n is from 1, 2, 3 onwards, otherwise 0, 0. two solutions, okay. They are repeated roots if n equal to 0, that is what you get. So, if these are repeated roots, first of all we will write, so the general solution is, general solution of that ODE, general solution is R of R is, so it depends if n equal to 0, if n equal to 0 you can write, if n equal to 1, 2, 3 onwards you have plus or minus n. So, you have for each n, so you can write, you can label them as Rn, capital Rn, capital Rn, okay. So, you have a capital Rn for each n is running from 0, 1, 2, 3 onwards. So, you have a capital for each n you have, so you are writing. So, if n is from 1 to 3 onwards, what you get is R power m is n. So, I call this some a n, arbitrary constant is also a solution, plus b n r power minus n as a solution if n is from 1 to 3 onwards, because they are repeated roots, they are actually distinct roots, plus or minus n is non-zero. If they are repeated roots, we know that it is actually some Cn. So, actually n equal to 0, if n equal to 0, so you call this some A0 r power 0. So, r power 0 is 1 plus B0, and you have r power 0 into log x, right. So, x power same repeated root, if m is the repeated root, if m equal to 1 1, what you get is r power 1 is one solution, r power 1 into log r is another solution, okay, just like x power 1 and x power 1 into log x. So, if you do the same thing here, so you have m equal to 0 0, so r power 0 is 1 and you simply get log r. So, log r is, this is your solution, these are the solutions you get, r power as a general solution. If n equal to 0, this is this, otherwise this is the solution. So, now you can see that you can write the product of these solutions. What is your actually, what you are looking for is u of r theta. So, for each n you can write as u of r theta, un of r theta. For each n, un of r theta is Rn of r, that is Rn of r is you consider a n r power n plus b n r power minus n times this is Rn of r into theta n of theta. So, theta n of theta is, so if theta n of theta is cos n theta and sin n theta, okay. So, cos n theta you can put cos n theta, so now you can see that cos n theta and sin n theta are solutions, okay. They are also linearly independent solutions, cos n theta, sin n theta. So, you can have a linear combination, okay. So, you can put linear combination. So, let us call this some Cn cos n theta plus Dn sin n theta. This is for n is from 1 to 3 onwards. So, if n equal to 0, you are left with a naught plus b naught log r times, if n equal to 0, only one constant. So, you have a Cn 1, so Cn into 1, so C0 into 1. So, C0 into A0, if C0 is an arbitrary constant, A0 is an arbitrary constant. So, I will just define into simply, okay, let us call this C naught times n equal to 0 simply 1. So, that is the only thing left, okay. So, you can rewrite this as, you can write Cn times this, you can take this Cn times out. So, what you get Cn into An, you can define a new one. So, let us call this An, small ans, let us call this big Cn and this is a big Dn. So, these are big C0, okay. So, now I am putting as a small Cn. So, capital An into capital Cn, I am calling it An, r power n, capital Bn into capital Cn is small bn into r power minus n into cos n theta plus Dn An I can call something else, small Cn r power n, Dn Bn, capital Bn, capital Dn I am calling some small dn into r power minus n into sin n theta. This is from n is from 1 to 3 onwards. Otherwise, here a naught c naught, let us call this a naught plus let us call this b naught into log r if n equal to 0. So, this is what is my un of r theta. So, you can superimpose all these solutions, you can write sum of un of r theta, n is running from 0 to infinity as your a solution. So, let u of b be the solution, of Laplace equation. Okay. So far we have not used any of the boundary conditions. Okay. So, we actually intrinsic boundary conditions, that is periodic boundary conditions we used, and we extracted the Sturm-Liouville problem with periodic boundary conditions. We derived these solutions and we superimpose them. This is what you see, that we assume that this is the solution. And what is this one? You can write u of r theta as now n equal to 0, you can write separately a naught plus b naught log r plus this sum I can put it as 1 to infinity a n r power n plus b n r power minus n into cos n theta plus c n r power n plus d n r power minus n sin n theta. Okay. So, this is the general solution what you so far. Okay. Now, you are on the annulus. So, let us use the boundary conditions. So, boundary conditions, let me use first u at r1 on the inner circle, u at r1 theta is equal to f1 of theta. So, what is this one? U at r theta, you can put it here. So, you will get u a naught plus b naught log r1 plus this sum, n is from 1 to infinity. Now, you can write a n small r1 power n plus b n r1 power minus n into cos n theta plus c n r1 power n plus d n r1 power minus n sin n theta, which is equal to, this is what is u of r1 theta, which is f1 of theta. So, what are your eigen functions? Cos n theta, sin n theta, and this is simply a function of, this is simply a constant. So, 1 into this one, this constant. Okay. So, this is 1 into this one. So, you have eigen functions are here. So, this is 1 and this is 1 and this is 1. So, you have a function of theta which is written in terms of all these eigen functions. So, that means I can get these constants by just by applying this dot product. So, I can apply both sides dot product with the eigen functions, then I can get these constants. So, start with a0 plus b0 log r1 equal to, you can simply integrate. So, dot product if you use this side is simply integrate from 0 to 2 pi 1 square 1 into 1 d theta. So, it is actually 2 pi. Okay. So, 2 pi times this equal to, or simply, so this will come as a denominator. So, you have a 2 pi. So, the numerator will be, so 1 divided by 2 pi into numerator will be that is the right hand side. So, 0 to 2 pi f1 of theta into 1 d theta. So, this is what you have. So, this is the one constant. Okay. This is 1, and now you can write for each n you can get this constant just by applying cos n theta both sides and integrate from 0 to 2 pi. So, if you do this one, so you will get a n r1 power n plus b n r1 power minus n. This is a constant equal to, again, so 0 to 2 pi, the right hand side is f1 of theta. I multiply cos n theta both sides and d theta and integrate, and the left hand side remains only will be cos square n theta. So, what is cos square n theta? Integral 0 to 2 pi. So, this you can find out. So, that is 1 minus cos 2 n theta divided by 2, that is simply 1 by 2. So, theta by 2 0 to 2 pi. Okay. So, what is this value? One plus, right, 1 plus sin square theta plus cos square theta minus sin square theta. So, 2 cos square. So, this is what it is. So, this is this you are integrating from 0 to 2 pi d theta. So, if you do this theta by 2, so half theta, that is 0 to 2 pi. So, this will not contribute. So, what you get is 2 pi by 2. So, you will simply have pi. So, I have again 1 by pi, you get this one. This is equation number 2. This is actually valid. You have infinitely many equations here. For each n you have one equation. So, you have this system of equations, and similarly you can get Cn small cn r1 power n, this constant dn r1 power minus n, this constant I can get it again. This time you will see that integral 0 to 2 pi again sin square n theta d theta. This is also you will get, instead of plus you will get a minus. So, you again finally contribution is same. So, you have 1 by pi integral 0 to 2 pi f1 of theta cos, instead of cos you are multiplying with sin n theta d theta. Again this is the system of, again n is from 1 to 3 onwards. So, these are the from these see you have 3 equations kind of thing, okay, 3 equations you can find a naught, a n, c n, or 3. So, you have unknowns are 1, 2, 3, 4, 5, 6, okay. So, now so far you got only 3 equations. I applied only boundary condition number 1. So, boundary condition 2 if I apply, so that is u at r2 theta equal to f2 of theta, okay. So, if I do this, so everything is same, instead of r1 you have r2, instead of f1 you have f2. So, you can have, there is these 3 things will be repeated, that is if I write this you get a0 plus b0 log r2 equal to 1 by 2 pi integral 0 to 2 pi. Now, instead of f1 f2 of theta d theta. So, this is the equation number 4, and similarly a n r2 power n plus b n r2 power minus n equal to 1 by pi 0 to 2 pi f2 of theta cos n theta d theta. This is equation number 5. Now, the equation number 6 is Cn r2 power n plus dn r2 power minus n, which is 1 by pi 0 to 2 pi f2 of theta sin n theta d theta. This is equation number 6. So, these 2 equations for 5 and 6 you have actually n is from 1 to 3 onwards, n is from 1 to 3 onwards. So, this is how you get, if you apply this, apply the boundary condition 2, you get this one. This is again you see you get the same similar type of equation, instead of f1 you get f2, instead of r1 wherever in this constants r1 you get putting r2. So, that is how I get these 4, 5, 6. Now, I have 6 unknowns, a naught, a n, c n and b n, d n, 6 unknowns, and I have 6 equations, okay. So, I can find all of them from these equations, linear equations, okay. So, implies I can get, so implies I can get by just by solve 1 to 6 to find 6 unknowns. What are the unknowns? A0, B0, AN, BN, CN and DN, that is it, okay. So, if you know AN, BN, CN, DN, so now I have the solution. So, solution now everything is known. This is the equation, this is the required solution. So, this is the required solution with now unknowns are given by solving this 1 to 6, okay. So, this is how you solve, this is the required solution of this Laplace equation. Now, I use these boundary conditions, what is the data on the boundary, on the circle, okay, both the circles in the annulus region. This is how you solve it. So far r power minus n is not a problem, because it is the annulus region. So, annulus region you have r1, r2 which are non-zero, so you do not have issue, okay. Now, let us from this problem let us extract the 2 remaining problems, so, okay. So, we solved this problem for the annulus region. If you want this circular, so let us say you want to solve this problem here. So, you have a 0, you have r1, okay. So, if you want this solution for this interior, this is the d, and you provide u at r1 theta equal to f1 of theta. So, this is your Laplace equation. In the inside del square u equal to 0, and this for this problem for the interior, and the d is interior of the circle. The solution is, so the only thing is you have to go here. So, you take here. So, this one what happens for the interior, you simply take r2. So, this is the general solution which we have, okay. So, the procedure is same. So, only thing is when you multiply, when you take this solutions, for example here. So, when you get the general solution of this r of r, what is r? R is between, now because it is a circle, interior circle, r is between 0 to r1. So, you have 0 to r1, and because 0 is involved. So, r is actually 0 to r1. So, as r goes to 0, this is going to become unbounded, but we know that at 0 this is a steady state temperature, temperature cannot be unbounded at the interior of the domain. So, suppose if you take a circular plate, initially you have you reach once you reach the steady state, once you reach the steady state of the temperature, steady state, when the temperature reach the steady state, it cannot be infinite at the middle of the point. Okay. So, for that Bn's will be 0, because of that now if you take this one, Bn's will be 0. So, Bn's will be 0, only left with this one. Similarly, this part will be 0, B0 will be 0, okay, because log r is going to 0, going to infinity as r goes to 0. So, that means this r of r cannot have will have unbounded solution if you allow log r as solution. So, that means the coefficient you should take it as 0. So, here you remove these two and a n r power n a naught, that is your r of r n. So, that you put it. So, once you know b n and b 0 or 0, so this part will be 0, and what you are left with a n c n, you call this a n r n, and here small b n, wherever b n. So, you get with r power minus n will not be contributing. So, similarly here, okay, this will not be contributing. What you are left with only 1, 2, 3. So, you have bn's will not be contributing, dn's will not be. So, this will be 0, okay, for the circular domain, where this is 0 to r1. So, you can apply the initial data. So, that is a boundary condition, that is at u at r1 theta. So, if you apply this, I do not have bn's, I do not have dn's, I do not have b0. So, what you are left with is a0 equal to this, I found directly here on. Similarly, a n r1 power n is this bn, because bn is 0, okay. So, that means I find a n directly. Similarly, cn I can find directly. So, I can just solve it. So, without bothering about the. So, if only thing is you just go back, look at the solutions. When you before you superimpose these solutions, you look at the circle. So, you allow now you allow because r is between 0 to r1, you have r equal to 0. So, r power minus n will not be contributing. Now, similarly, if you consider exterior of the circle, now you take the domain is exterior of the circle, so domain is D. So, r is between r1 to infinity. So, at infinity, so you want when the, so if you have a infinite plate with a hole and it reached a steady state, okay, initially at some you give a, so it is at a steady state temperature, okay, it is a plate, infinite plate with a hole, that is the exterior domain, exterior of a circle, okay. So, at infinity it should be temperature cannot be unbounded. So, that means you should remove this one a n r power n, as r goes to infinity u of r theta should be bounded, okay. At least you cannot say it goes to 0, because it is infinite plate, you can expect it actually it should go to 0. So, that if that is needs to be 0, only bn's will be the solutions, r power minus n will be the solutions, not r power n, okay. R power minus n will be the solutions, n is running from 1 to r. So, if you have in this domain, because r goes to infinity, you cannot be, you have to be 0, u has to be 0. So, that means you have to remove, instead of bn's, you have to remove an's. Similarly, as r goes to infinity, log r is also becoming infinity. So, that means b0 here, b0 you have to allow it to be 0, okay. So, everything is same, only an's, instead of bn's, now you allow an's to be 0. So, you have finally instead of bn's you have an's you allow it to be 0 and b is 0 0. When you take the combination, when you take the linear superposition, when you take the sum of them, so u n of r theta will be without an's and without cn's you will get that, and without b0. So, these are the without this you get a solution. Now, instead of bn's you will have a bn's, without this term you will have this, okay, for a external exterior of the circle, that means it is unbounded domain. So, it is like an infinite plate, plane plate, so plane is like a take a plate and you have a hole in it, that is a circle, okay. On the boundary of the circle you have to provide the data. So, this is what is the solution without cn's and an's, without bn's, b0, okay. b0, an and cn will not be contributing as a final solution. Now, you apply the initial data, what you are left with is b0 is 0. So, you get anyway a naught equal to, so you get a naught from equation number 1. Now from equation number 2, because ANs are 0, so you can get Bn directly from this equation number 2. From Cns are not there, equation number 3 will give you Dn. So that is it. So if you can solve both the problems, either this or you consider this exterior domain. So as your D, and you provide the data here. So this is a boundary B, u at r1 theta equal to f1 theta. Okay. So here del square u equal to 0. So these are the two problems you can simply extract from this method. Actually not from the exactly from this annular region we have not. So this is the solution you used. If you want the exterior thing, you just have to allow R2 goes to infinity. Okay. If you want this circular problem, you have to allow R1 goes to 0. So that sense you can here also you can get it. So directly you can, once you get these solutions, you can allow that R1 goes to 0. You can, that is also one way. Okay. So you allow R1 goes to 0. So you cannot have unbounded things. So the Bn's won't be contributing. Okay. So you will have something like that. So you don't really just don't take the limits. Instead, you part of the solution procedure which you used for the annulus region you use, where Rn of R and theta n of theta. When these functions, when before you superimpose, you consider the domain. R is the, if you consider the interior of the domain between 0 to R. So you consider, instead of R is between R1 and R2, you consider what is the domain for the interior of the circle, that is now 0 to R. Now you remove whatever is not. So at 0 it should be bounded. So your solution R of R will be little different. Similarly, but theta n's are same. So theta n's are simply cos n theta sin theta, this won't be changed. Okay. Only R and of R will be changing. This is how you can solve interior of the circle and exterior of the circle just by the procedure of this annular region. Okay. So now you know that how to solve this these three problems just by looking at the procedure of this annulus region. Okay. So in the next video we will see how we will look at the problem in the sector like this. If a sector means this is a circle, this is the sector. Okay. If this is the 0, let me draw properly. So if this is your circle, 0 is the center, and you take this one part of the circle, that is called sector. So in this I consider this is at R1, this is the interior circle. So you have one more circle here. Okay. And this is your R2. So I consider this domain. That means if I draw again, so next video I will do this one. So this is how I do. Okay. So this is the domain I consider. So you have theta is here, and this is your so R. So this, because of this is 0. Okay. So you have this line with theta 1, and because of this line let us say, so this line with theta 2. Okay. So your domain is actually this one. So here we try to solve this. So this Laplace equation is satisfied here. The boundary is now, this is one boundary and this is another boundary. So B is this, B is this. So on this B we provide a data. Okay. So Differential data, that means you provide the temperature u at R2 of theta, theta is between theta 1 to theta 2 equal to okay. So some function f1 f2 of theta, because at R2. Okay. Similarly here you can provide u at R1 theta as f1 of theta. Theta is between theta 1 to theta 2. Earlier for the circular domain, say circular domains between 0 to 2 pi. Now here is only because it is a sector, so you have to take theta is only between theta 1 to theta 2 to theta 1 to theta 2. Theta 1 is smaller, so theta 2 is bigger. So this theta is actually theta 1 to theta 2. So what you expect is you have to, so what is the boundary now? So this is one boundary and you have a boundary here. So this is the boundary for theta. Okay. So at this theta you have to provide 0 boundary conditions, because you want to use the Sturm-Liouville problem. You want to extract the Sturm-Liouville problem and solve it. So for that you provide the data here. So this is from R theta 1 equal to 0, and here u at r theta 2 equal to 0. Okay. So, with this kind of problem, so this will give you, this will allow you to get the extract the Sturm-Liouville problem, and then finally use these boundary conditions to find the unknowns involved in the superposition of all the solutions. Okay. So, we will look at this general problem in the next video, and then now you take theta equal to 0, theta 1 is 0 and theta 2 equal to 2 pi, then your domain will be this one, circular domain, semicircular domain. Okay. And if you want in the quarter plane, you can also get this. If this is your domain, you take theta 1 equal to 0 and theta 2 equal to pi by 2. Here it is 0, theta 1 equal to 0, theta 2 equal to pi. Okay. This is pi, here 0 to 2 pi. So, different domain. So, if I do this and again you have to allow r1 goes to 0. Okay. So, earlier, so here r is between r1 and r2. So, here r is between 0 to r2, that means r1 you have to take 0, here also because it is involved, 0 is involved here. So, r is between 0 to r2. So, this is how by looking at these domains, and so you can extract the Sturm-Liouville problem and then make use of. So, once you solve this, we will solve this in the next video for this general sector, part of the sector, okay, circular sector. So, if we once we solve this, we can actually solve these two problems again. Okay. So, we can solve once you solve this one and you can solve 2, 3 as similar to what from the, you can actually see the special cases of 1, 2 and 3 are special cases of 1 problem. Okay. We will see this in the next video. Thank you very much.